Okay, we're going to go through some series convergence divergence questions. The only tool we have at this point in the class, only two tools, are the integral test. We also have the nth term divergence tester. So most of these are going to be aimed at the integral tester. See how this works? And we've got a bunch of series, and all we're trying to figure out is if the series is convergent or divergent. That is, does it converge or diverge? First one is the series where we go n equals 2 to infinity, 3 over n log n. So let's just write that down. So we've got a series, n equals, I believe it was 2 to infinity. We had 3 over n natural log of n. Here. We want to figure out if this converges or diverges. So what the integral test tells us is, well, don't do this as a series, do the sort of associated integral. So we can do an integral of 3 over n log n, except instead of n's, I'm going to put x's here. I guess I could use n, but I feel more comfortable with x in an integral. We're used to that. Do a dx. And then my bounds here, I'm going to start at some constant, and I go up to infinity. So this constant down here, you can put anything you want, as long as your function is well behaved. We probably don't want to do x equals 0, because we're dividing by 0. Also, if you put in an x equals 1, you'd get natural log of 1 is 0 in your denominator. That would be bad. So let's go ahead and put in something bigger than 1. How about 2, which matches up here, but that's not strictly necessary. I could put in a 6 or an 8 here, or whatever. Just something bigger than 1 is what we need. Okay, so let's do this integral. What we're going to get, well, how do you do this? Well, let's see. Before I do this, I'm going to work on the indefinite integral, 3 over x log x dx. I'm going to approach this one using u substitution. So I'm going to scroll down a bit here. I'm going to do a u equals natural log x. So what I'm seeing here is a natural log. I'm hoping if I let u be natural log x, things will work out. Du is then 1 over x dx. Note, this 3 over x natural log x we can rewrite as 3 times the integral 1 over natural log x times 1 over x dx. So this is the other reason I chose to make u natural log x, is because I saw this x in the denominator, so I know the du would want essentially an x in the denominator. So it seems like u equals natural log x would likely work out. Now what we get is 3 times an antiderivative. 1 over natural log x is 1 over u. 1 over x dx is du. And then you do that antiderivative, and you get natural log of u plus c. And then u is natural log of x. So you get natural log of x plus c. So that was our antiderivative here. It's sort of our indefinite integral. Now to do the definite integral, I know now, whoops, at some point I lost my 3. I know I should get 3 times something. So down here, I should get equals 3 natural log u, 3 natural log x. So I know now here that an antiderivative is 3 natural log of x. And I'm just going to plug in 2 and infinity. And you could write this as a limit statement, but this is sort of more efficient here. When you plug in infinity, you get 3 times natural log of infinity. You plug in 2, you get 3 times natural log 2. Now here's the thing. This 2 at the bottom, 3 natural log of 2, if I plug in any number bigger than 1, natural log 2 is some number bigger than 1. Or sorry. Well, actually, no, not bigger than 1. So it's just some number, and then I take natural log of that number, positive number. Let's see, is it a positive number? Yeah, if 2 is bigger than 1, if the thing I plug in the bottom is bigger than 1, natural log of that will be positive. So I'm getting natural log of a positive number. I'm going to get some finite number here. So this minus 3 natural log of 2 does not affect the convergence of our integral here. It's just something added on. It affects the value it might converge to, but it's still going to be convergent or divergent, regardless of what number you plug in for 2. But then on the first term, natural log of infinity is going to go to infinity. And so I'll get natural log of something going to infinity. That's going to give me an infinity. So this whole thing is infinity minus some finite number that's infinity. And that tells me that my integral diverges. So what I have now is that, let's just sum this up down here, is I did, via just sort of directly computing the integral of 3 over x natural log x dx from 2 to infinity diverges. And essentially, if we check the other conditions of the integral test here, we can get that the series converges. So the other conditions here are technically, we need that 3 over n log n should be positive for n greater than 2. Well, that's clearly the case. So now these, I tend to get sloppy and forget these because most of the things we're doing, these will be true anyway. But 3n log n is greater than equal to 0. This is for n greater than equal to 2. Note if n was less than, say, 1, you'd get a natural log of 0, or sorry, natural log of 1 would be a divide by infinity. You could even get a negative natural log. But once you get to 2 in here, you're going to get 3 over something positive times something positive. That's clearly going to be not just greater than equal to 0, but greater than 0. We also need, really, 3 over n log n is, so I'd say non-increasing. That is, it's really decreasing, but if it's flat, that would work out as well. And that's really easy to see because as you make, 3n natural log n, as you make n get bigger, the denominator, both factors in the denominator get bigger, so the denominator just gets smaller and smaller. Or sorry, the denominator gets bigger, so the fraction gets smaller and smaller and smaller. That's really all we need. So these two things, technically, here in parentheses, these two things, technically we should be checking all the time for the integral test. To be honest, I kind of forget about them because they're generally true unless we've got some kind of crazy situation going on that's perhaps created to show, hey, we actually do need to check these. But most of the time in practice, they're going to be true and pretty easy to see. Okay, in any case, we get that this integral converges. Both of these two things are true. And what the integral test tells us is that n equals 2 to infinity of 3 over n times natural log of n not converges. Does the same thing as the integral. Diverges by the integral test. So that's our setup. Now, again, the general picture you should have in your mind here is that if I graph, so I'm not even going to do a nice job of the graph, but if I graph y equals 3 over x natural log x, and I start at 2, and I look at this area here, this area under the curve as I go to infinity is infinite. So our red area is infinite here. Well then, let's maybe do this in blue. This series here, what's this? It's summation n equals 2 to infinity 3 over n log n. If you plug in 2, you get 3 over 2 natural log 2 plus 3 over 3 natural log 3 plus 3 over 4 natural log 4, and so on here. So what's going to happen here is this 3 over 2 natural log 2, well, that's if I plug in 2 for x here. So what I'm going to do is I'm going to go to 2, to 3, to 4, to 5. This first term, this first term, 3 over 2 natural log 2, that's going to be a rectangle that's got this sort of green area here. So that's really the height is the function value, plug in 2, that's our 3 over 2 log 2. The width of that rectangle is 1. So we're saying here is that this green rectangle has area that's equal to this first term. This next term, 3 over 3 natural log 3, would be really this second rectangle's area. Function height, or the height of this rectangle, is plug in 3 for x in our function. That's right there. And then you just sort of do that. We could get a third term, 3 over natural log 4, would be this rectangle height here. So we get a green plus a blue plus a purple rectangle areas. And if you look at this, what's going to happen here is that the area of these rectangles is clearly bigger than the area underneath the curve here. That's just because the rectangles include the area under the curve and then some extra stuff up above. So it's bigger. And what that tells us here, essentially, is, well, the area here is bigger, and that tells us that the integral from 2 to infinity, 3 over x log x dx, well, this should be smaller than the series here. And since this goes to infinity, here, that integral, because that integral diverges, we actually show it diverges to infinity, but given the conditions on the function, if this integral diverges, it has to diverge to infinity here. and that means that this series has to also go to infinity. So essentially that's how the divergence part of the integral test works. The convergence part would be you could take this series here, and instead of writing these over the top here, so what we could get, let's draw a different picture, is you could also essentially get that the sum of the series is less than some integral. Now, what we're going to do to make that work out in this case is we're going to get rid of this first term. Now, you can do that for convergence because the first term does not affect convergence. So if I did n equals 3 to infinity, 3 over n log n, if that converged, 2 to infinity would converge because, like, if I did 3 to infinity, I'd get some value, and I just add whatever 3 over 2 natural log 2 is to that. So what I'm going to get in that case is I get a picture of my red curve here. And I get sort of my area at 2. I have this area underneath. Now, if I was going to... Whoops, sorry. Let me draw it again. Let me start over here. So here's my red curve. Here I've got some area underneath. And if I was going to show that my series converges, what I would get here is that I need this to be a finite area under the curve here. Now, it's not for the function we chose, but suppose you had a function where it was there. Well, then what you would do is you'd take this blue rectangle, start that at 3, 4, so we go up to 3, and now you'd sort of draw the corresponding rectangle that's under the curve. So this blue one, really it's the same area, just shifted to the left one. And then I guess this purple one, 3 over 4 natural log 4 would be here. And if you think about that, what we're showing here in that case is we get n equals 2 to infinity, 3 over n log n. We're, well, not this, bounded above. We're starting at 3, so let's do it here. N equals 3 to infinity, 3 over n log n. This is bounded above by this integral here. So 2 to infinity, 3 over x log x dx. Now, because this integral is infinite, that really doesn't tell us much about the series. We're saying it's less than equal to infinity, but, I mean, that's true for everything here. So that didn't really tell us anything. But if we could get that the series converges, or sorry, the integral converges, that'd mean we get a finite number here, and then for the integral, so we know this series would have to go to a finite number as well here. So that's really sort of the idea of the integral test, is you can sort of bound a series either below or above by an integral. That integral can be chosen to have essentially the same function that you're integrating, the same integrand as the sequence inside of the series. And because you can bound above or below, if you set things up right, you're going to get that the series and the integral either both diverge or both converge. That's sort of the reasoning behind the integral test. You don't actually need to do all this pictures and sort of inequalities here. You just set up the integral, figure out if it diverges or converges, and then the series does the same thing. Okay, but it's nice to explain that sometimes. Okay, next question here. So let's go look at number 2. We have an series, n equals 1 to infinity, of natural log n over n. So let's write that up. So number 2 here, got a series, n equals 1 to infinity, natural log n over n. Now, this one, I'll be honest here, I would probably use a comparison test once we get there. There's something I can look at this and tell right away whether this converges or diverges. Right now, we have to use an integral test. So what we're going to do here is I'm going to do an integral of natural log x over x dx. Going to go to infinity, and I can start this at 1 or 2 or 3 or 10 here. It doesn't really matter. You just sort of get extra terms at the start of the series, but those finite number of extra terms don't matter in terms of convergence. So I'm going to do this integral. Here, let's just do a u. Same trick as before. U is natural log x. du is 1 over x dx. So I see a natural log x. Often letting u be natural log x can get rid of that natural log, which is useful. Also, I saw an x in the denominator. Tells me that the du will be 1 over x if u is natural log x, and that just tends to work out well. So what I'm going to get is natural log x gives me a u. The over x dx, that'll give me a du. My bounds, I'm just going to leave for now. I'll switch back to x's. Integrate, I get u squared over 2 from some x values. And I'm going to put in the u is natural log x. So I get natural log x squared over 2. and then my bounds are 1 to infinity. So what that gives me is natural log infinity squared over 2 minus plug in 1, natural log 1 squared over 2. So this term with the natural log 1, natural log 1 is 0, that's going to work out to be 0, but it's something finite. So if the 1 was a 2 or an 8 or a 37, no matter what, this would be finite here, which means that really it doesn't affect whether the integral converges or diverges. We're concerned about this term with the infinity. And here we want to think natural log of infinity, that goes to infinity, infinity squared, this goes to infinity. And what that means is that the integral from 1 to infinity, natural log x over x dx, diverges. And essentially what that tells us here is that the series n equals 1 to infinity, natural log n over n also diverges. So that's really our answer. All right, next one. Let's look at 3. Now we have 1 over n times natural log of n squared. So we're going from 2 to infinity. So it's number 3. It's a pretty ugly 3. And we get 1 over n times natural log of n squared. Here. And again, I'm going to use the integral test here, mostly because I see a natural log n and then an n in the denominator. And so I think, oh, if I set up my integral, say from 2 to infinity, 1 over x natural log of x squared dx, I can let u equal natural log x. And then du is 1 over x dx. So if you just have this series here, before I even bother with the integral test, I'm going to think about, is there a substitution I can do? I think, oh, if I let u be natural log of x, I have sort of the x in the denominator, so this substitution is promising. Let's work this out. We get an integral from something to something. Some pretty poor question marks. We get 1 over, see, natural log of x, that's 1 over u squared. And then the x I'm going to pull over with the dx to form du. So this is u to the negative 2. Gives us negative 1 over u, or u to the negative 1 over negative 1. Evaluated from something to something. And then convert that back to x's, negative 1 over natural log x from 2 to infinity. So what we get here, let's see, we plug in infinity, negative 1 over natural log infinity minus a negative 1, that's going to be plus 1 over natural log 2. Okay, so what happens here? 1 over, well, negative 1 over natural log infinity. Natural log infinity will go to infinity, so this first term goes to 0 here. So I get 0 plus 1 over natural log 2. So this whole thing is 1 over natural log 2. And the key thing here is this is finite here. So this is a finite value. It did not go to infinity. And what that means is that the integral 2 to infinity, 1 over x, natural log x squared dx, this integral converges. Because we got a finite value. This integral actually converges to 1 over natural log 2. And what our integral test tells us, because this is going to be behaved well, that 1 over n natural log n squared is always positive. Also, it's going to be decreasing as n gets bigger and bigger. These terms get, well, the terms inside get smaller and smaller because the denominators get bigger. And what that tells us is that our series, n equals 2 to infinity, 1 over n times natural log n squared, pretty poor square, also converges. Now note, one thing this does not tell us here is what this series converges to. You might be tempted to think the series should converge to 1 over natural log 2, but that is not necessarily the case. All we've typically shown is that, except for getting rid of maybe the first couple terms of the series, that this series is less than 1 over natural log 2, or less than or equal to 1 over natural log 2. So we don't get a value of what the series converges to, but we know the series converges. Next one. Okay, here we've got a, let's see, series n equals 0 to infinity. We're doing e to the negative n. So we're doing a series n equals 0 to infinity, e to the negative n. And sometimes I would think about this in series land as 1 over e to the n here. So it makes me more comfortable looking at that as a series, but they're equivalent here. Note, you might be worried about plugging in n equals 0 because you have something in the denominator. Well, e to the 0 is 1, so that's going to be just fine here. Again, later on, we'll get something where I can tell whether this converges or diverges pretty easily here by comparison test. There's also something we did earlier with a geometric series. You could use that to show this converges and actually get a value that it converges to. We might do that at the end here. But let's do the integral here. So the corresponding integral, let's go from, how about 1 to infinity? You could do 0. It says e to the negative x dx. So this substitution, I just do u is negative x, du is negative dx, and I get an integral from something to something. I get a e to the u, and then I get a du, but then I need the negative, so I'll put that out in front. So I get a negative e to the u du. Integrates to negative e to the u with some bounds. So this gives me a negative e to the negative x going from 1 to infinity. Here. Okay, so I get negative e to the negative infinity plus minus a negative, so minus because it's the bottom term and then the negative out in front, e to the negative 1. Now, negative e to the negative infinity here, that's actually going to go to 0. You might see that a little bit more easily if I write this as 1 over e to the infinity plus e to the negative 1 is 1 over e. So this is 0 plus 1 over e. This equals 1 over e. Now, whatever this is finite, and that tells us our integral, 1 to infinity e to the negative x dx, that integral converges. And that means our series, n equals 0 to infinity, e to the negative n, also converges. Here. And again, we know the integral we wrote down converges to 1 over e. If you'd done an integral from 0 to infinity, you actually get this to be 1. But that's not necessarily, and probably not, the value that the series converges to. So we know the integral and the series both converge, just not to the same value. Here. Now, I said this at the beginning of the problem. We can actually evaluate the value that this series converges to. Here. I just need to recall that if you have a geometric series, so if we have r, absolute value r less than 1, and we have a what's called a geometric series, so it can be geometric without the absolute value r less than 1, but the formula I'll give will only work for absolute value r less than 1. So if you do a summation n equals 0 to infinity, r to the n, this is 1 over 1 minus r, if absolute value r is less than 1. Okay, so what we had maybe didn't look like that here. Well, it sort of did. We had a summation n equals 0 to infinity, e to the negative n, and we rewrote this, n equals 0 to infinity, 1 over e to the n. And you could write this again as n equals 0 to infinity, 1 over e raised to the n. Now, 1 over e is less than 1 because e is like 2.7 something here. So this is going to be 1 divided by something bigger than 1. The 1 over e is really our ratio. That's less than 1. And so what that tells us here is because absolute value r is less than 1, because it's the geometric series, that tells you the series converges. So you could just say, hey, 1 over e is less than 1, thus the series converges. Skip the integral test altogether. But even more so, we can say what this converges to is 1 minus 1 over e. And then probably here I'd multiply the top and bottom of this by e, because I don't like that 1 over 1 minus e, and sometimes nice things happen. You get e over, distribute the e, you'll get e minus 1. So not only does this series converge, but it converges to e over e minus 1, which is stronger information here. Note, that's not the same thing as 1 over e that we got here. We got something different there, which is typical here. Next one. Whoops. Okay, so number 5 here. Let's see. We have a series. Let's see, it's n plus 4 over n squared plus 8n plus 3. So number 5 series, we had n plus 4 over n squared plus 8n plus 3, and I'm thinking it was 1 to infinity. Okay. Now, this one of the nice things about the integral test, it's maybe different than some of the other tests. I don't have to sit here and try and think, do I think this series converges or diverges right away? So it's always just sort of the same kind of test here. So what I'm going to try and do is do an integral. We'll get to some stuff later on here where you can do this right away. So I'm going to do my integral. How about 1 to infinity, x plus 4 over x squared plus 8x plus 3 dx. So we want to know if this integral converges. So what I'm going to do is, it's actually going to work out to do a u substitution here. So I'm going to do u equals x squared plus 8x plus 3. So that might seem a bit weird, but then du would be 2x plus 8 dx. Note that's 2 times x plus 4 dx. Note the x plus 4 on top. There's my x plus 4 here. So what I'm going to get is an integral. Let's see, the 1 over x squared plus 8x plus 3 is 1 over u. I can take the x plus 4 times dx. Almost gives me du. I'm missing the 2. So I'll get a 1/2 du. And then bounds or something in terms of x. You could convert them by plugging in 1 for x in here and infinity for x here. I'm just going to convert back to x and do things there. So what I get is 1/2 antiderivative of 1 over u is natural log, really absolute value u. Here things will be positive. Whoops, don't need a plus c. Bounds are, I don't know, something for u's, which I'm not going to bother with. And then I get 1/2 natural log. The reason I cannot bother with them is I'm going to convert back to x. So this will be x squared plus 8x plus 3 here. And then I'm doing x goes from 1 to infinity. So I can do my integral directly. I get 1/2 natural log. Plug in 1. I'll get 1 plus 8 plus 3. That's 12. Again, I don't really care that that's 12. I just care that I got some finite value here. And natural log 12, yeah, I could simplify that maybe somehow, but I don't really need to. And then minus 1/2. Oh, sorry. No, not. So this was worrying me because when I did minus 1/2 infinity, here's what, I made a mistake here. I'll talk about this in a bit. But I was going to get a negative infinity. And that's clearly not correct because we have something that's always positive and we're adding up a bunch of positive things. It can't give me a negative. So what I did wrong is I plugged in the bottom bound first and then the top bound. So what I should have gotten here was when I plug in infinity, I get the 1/2 natural log infinity. And then I plug in the 1, I get minus 1/2 natural log 12. Again, the minus 1/2 natural log 12, that's some finite number I'm subtracting. Natural log infinity goes to infinity. This whole thing is infinite. And what that tells me is that the integral from 1 to infinity, x plus 4 over x squared plus 8x plus 3 dx, this integral diverges. Really, it went to infinity. And that tells me my series, n equals 1 to infinity, n plus 4 over n squared plus 8n plus 3 also diverges. So that it's probably the straightforward way that most people would do this at this point in time. Now, later on, people will do a comparison test, which is like the comparison test for improper integrals here. Maybe do a limit comparison test or a direct comparison test. But so that might be something else people would do here. I mean, essentially, we'll get to the point of saying n over n squared is 1 over n, and then we know that the series n equals 1 infinity 1 over n will diverge, and so essentially this will diverge. It's sort of what's coming up later on. We don't really have that theory yet. But what we do have is we have a limit comparison test for definite integrals. So this integral here, we evaluated directly to say that this diverges. What you can do instead, let's see if we can copy this whole thing out. Edit, copy. Let's put this down here. Edit, whoops. Edit, paste. So we can do this integral instead. Well, we're not going to evaluate the integral directly. I just care, does it converge or does it diverge? Here. What you could do is use the limit comparison test for improper integrals. So you can use that here. Don't forget about some of these techniques we had. And what that allows me to do is instead of doing this integral directly, which wasn't that bad, but imagine like we didn't get an x plus 4 here, we get an x plus 3. What if this was x squared plus 6x plus 3? Well, then you would get you could maybe pull off an x plus 3 and then get a plus 1, and then you could think of x squared plus 8x as completing the square and then sort of do a substitution and you get an arctangent out of it, and it would work. It'd just be a lot of, sort of stuff to do. So instead of that, you can say, well, I don't want to do this ugly integral. What I'm going to do instead for my integrals is take a limit as x goes to infinity. I'm going to do x plus 4 over x squared plus 8x plus 3. And I'm going to divide that by what x plus 4 over x squared plus 8x plus 3 is basically equal to. So I have to kind of get used to doing this here. And essentially, as x gets big, really the x plus 4 is essentially just the x. And the x squared plus 8x plus 3, the x squared will dominate. And so I'm going to compare this with x over x squared, or just 1 over x if you want to simplify it. But I take the leading term on top, leading term on the bottom. Generally, that'll work if I've got polynomials. So I get a limit as x goes to infinity. You can now sort of take the reciprocal of your denominator and multiply. We'll get x squared times x plus 4 over x times x squared plus 8x plus 3. And this is then a limit as x goes to infinity of x cubed, nope, not x squared, x cubed plus 4x squared over x cubed plus 8x squared plus 3x. And then you could use L'Hopital's rule or divide the top and bottom by x cubed, or just knowledge of rational sort of functions here. And know as x goes to infinity, I've got degrees the same top and bottom. This is going to go to 1. So this is my limit L. And L was a number, finite number, that's positive, something between 0 and infinity, strictly between. And what that means is that the integrals from 1 to infinity, x plus 4 over x squared plus 8x plus 3 dx, and the integral from 1 to x, x over x squared, note that's just 1 over x dx, that these two integrals either both converge or they both diverge. So if you did things this way, you could have said, I don't want to do this complicated integral. I'm going to do this limit here, and this may look like a lot of work, but you'll get to the point eventually where you can say, oh, this is essentially 1 over x, and I can take my limit, and that's 1, and do that pretty quickly here. And then you say, instead of doing this ugly integral here, uglier by comparison, I do this somewhat nicer integral. And then you do this integral, and you could even recognize that as a p integral. Know that that diverges because it's 1 over x to the p with p less than equal to 1. So what we have here is that one diverges, and so they both diverge. And you could get that integral diverges that way without having to do the integral directly. Now again, it's not necessary. This one, writing it out, seems like it might be more work to do things this way than doing the integral directly. But if I change that 8x to a 6x, or the x plus 4 to an x plus 3 here, all of a sudden you might like this method a lot better. This method isn't going to get any harder by changing 8x to 6x. The integral will, because things won't match up exactly. Next one, last one here. We have integral, or sorry, not integral, series n equals 2 to infinity n over e to the n. So this is number 6. I'm going to do a series n equals 2 to infinity n over e to the n. Again, we may get tests later on that would perhaps suggest what to do here. This one, probably a ratio test, might work pretty well here, give you an answer right away. Perhaps a comparison test here. But we're going to do this as an integral here. So that's really our goal, is we want to do an integral test. And this one's going to be a little bit annoying, something you should be able to do, but it'll take a little bit of work, and so we'd prefer to sort of not do work if we don't have to here. So that's why we might want some more tests later on. So what we're going to do, how about an integral from 2 to infinity, x over e to the x dx. So what do you do with this? Well, what I'm going to suggest here is rewriting this as x times e to the negative x dx. And if you do that, you have something times something, sort of a product, makes you think probably integration by parts will work here. And this seems like it should work out. So I'm going to do integration by parts. I'm going to do u equals x. Do dv then is e to the negative x dx. and then du is dx, so sort of the x got simpler, kind of got replaced by a 1. V, if you integrate e to the negative x, you get negative e to the negative x. So that didn't really get much more complicated. You got a negative out in front, but that's just a constant. So what we get is uv, that's negative x e to the negative x. Now, because this is a definite integral, you evaluate those from 2 to infinity, minus the integral from 2 to infinity. So this was uv minus v du. So that's minus a negative e to the negative x dx. Okay, so what we get is negative x e to the negative x. I'm just going to leave this evaluated at 2 to the infinity. I could do that later. Let's see. Antiderivative e to the negative x is again a negative e to the negative x. You sort of have two negatives. You pick up a third one. Get a minus e to the negative x from 2 to infinity here. Okay, now let's plug in and see what happens. Do we get a finite value or an infinite value? When you plug in infinity, you get negative infinity times e to the negative infinity. Well, that's infinity times 0. So that's an indeterminate form. So we actually don't want to write infinity times 0. We're going to actually have to take a limit as x goes to infinity of negative x over e to the negative x. So what we get here, let's erase this here. Do a negative limit as x goes to infinity, x times e to the negative x. Then you plug in the 2 plus 2 e to the negative 2. And then minus e to the negative infinity. That's going to go to 0. And then plus another e to the negative 2. So this e to the negative infinity goes to 0. So this all rests, and we have a finite value, finite value. So the convergence of our original series rests on, does x times e to the negative x go to a finite value as x goes to infinity, or does it go to an infinite value here? So let's look at that. If I do a limit as x goes to infinity of x times e to the negative x, I'm going to kind of take this x e to the negative x and sort of go backwards here from what I did before. I'm going to rewrite this as x over e to the x. Now, what will happen if you plug in x going to infinity, this is going to be an infinity over infinity here. So you get infinity over infinity. So this is a chance to use L'Hopital's rule. This is an indeterminate form. So what you get here, let's split that up here, is you get a limit as x goes to infinity. What you do is you take the derivative of the top with respect to x, that's 1, over the derivative of the bottom with respect to x, that's e to the x. So this is 1 over infinity. That's going to go to 0. Here, so you use L'Hopital's rule, and you figure out x times e to the negative x goes to 0. Essentially, e to the x goes to 0 faster than x. So we get here, this goes to 0. So we really end up with 2e to the negative 2. So a 0 plus 2e to the negative 2 minus a 0 plus e to the negative 2. I guess that's 3e to the negative 2. Don't really need to simplify that because all I care about is this is a finite number, 3 over e squared. Something. I don't care what it is. And that tells us that the integral from 2 to infinity, let's see, x over, let's write it this way. What do we have? X over e to the x dx. This integral converges. And that's going to tell us that our original series, summation n equals 2 to infinity, n over e to the n, also converges. Here. And that's by the integral test.